Hello everyone, I'm Bohan. I'm a CA for 173, and today we'll be going over tutorial 6, which covers induction and summation. So, for the first problem, we're given a formula to find the sum of the first n numbers, and we wish to find a closed form solution for the sum from I equals 3 to k of k plus 2i. So first what we can do is we can split the summation into two separate summations, one involving this k term over here and one involving these two i's over here, because addition is commutative and associative. And what that will do is that will simplify the summation so that we have the terms in a bit of a nicer form. Alright, so I'll take the sum from I equals 3 to k of k plus 2i is equal to the sum from, and these will have the same bounds, of k plus the sum from I equals 3 to k of 2i. Right? This term on the left, notice that our indexing variable is I, and this term on the left has no dependency on I, which means that this sum just looks like k, etc. And the number of k's that we have is just the number of times we index this, which is in this case k minus 3 plus 2, which is k minus 2. This whole thing can just be expressed as k times k minus 2. Now for our expression on the right, what we can do is first we can factor out a 2i, because this 2i is simply just going to multiply everything in the summation by 2, and we can just factor that out. So this is just 2 times the summation from I equals 3, I equals 3 to k of I, right? And now this looks like what we want, except the bounds are off. So what we can do is we can adjust what these bounds are. So our lower bound, we want to start at 0. And our upper bound, we want to start, in this case, our upper bound would have to end at k minus 3. Oh, and I've forgotten an underscore. So here, now we want to start from I equals 0, and our end bound would have to be k minus 3, because we need k minus 2 terms in the summation. Right? Our old summation started from 3 to k. Our new term starts at 0, so it has to go to k minus 3. And each term in here will have to be I plus 3, because now that we've adjusted I by decreasing it by 3, every term in the summation will have to have an additional 3 added to it in order to match the terms of our original summation. And we can factor this out in a very similar way as we did originally, where we can split this up into two summations. So now we get just 2 times the sum from I equals 0 now to k minus 3 of I, plus 2 times the summation from I equals 0 to k minus 3 of 3. And I have, again, forgotten my underscores, and this should be a minus. My apologies. But now, this thing on the left here now has a, we can now use the formula that we're given at the beginning, because it matches, the form matches exactly what we have up here. So this is just equal to k plus 1 times k over 2 if we plug in k minus 3 for k. Right? So we can say that this is equal to 2 times, and then if you plug in k minus 3, we get k minus 3 plus 1, which is k minus 2, times k minus 3 over 2. Right? So that's what this is equal to. And I'll just simplify this into k minus 2 times k minus 3. The thing on the right here, this 2 times the sum from I equals 0 to k minus 3 of 3, is very similar to what we saw before, where every term, this is just a 3 added together a bunch of times. And just like we saw before, we have k minus 2 terms here. So this is just equal to 2 times 3, which is just 6, times k minus 2, because there's k minus 2 numbers. Right? Now going back to our original summation, originally we wanted to sum these two summations up here. Remember? So we'll just copy paste this down again, and then we'll use the closed forms that we got for both of those parts. Right, so this is equal to, the first part, the left side, is k times k minus 2. This should be k times k minus 2. And then this other part that we got is k minus 2 times k minus 3 plus 6 times k minus 2. And if we do some algebra, I believe we should get that this equals 2k squared plus minus k minus 6, which is our final answer. Yeah, so you could have done some, let me see if this will make it a bit more condensed. No, it will not. Okay. So yeah, if you were writing this on an exam, you could write some clarification here. So just explicitly state which parts of the equation you're trying to solve. But in general, this would be the general idea of how to approach it. Okay, let's move on. All right, the second question is an induction question. So what we need to do is we need to prove this formula is true using induction. So first, what we need to do is we need to decide what we want to induct on. In this question, there's really only one thing that changes, which is how many terms in this summation there are, and that's all determined by n, which means in this problem, we'll have to induct on n. Now, for every induction problem, there are two cases, or there are two parts. Number one is your base case, and number two is your inductive case. All right, so your base case should be proving that for the smallest possible value of n, this formula holds. Right? Here, because we're restricted to only positive integers, the smallest case of n is 1. Now, for n equals 1, we're taking the sum from k equals 1 to 1 of 1 over k times k plus 1. And this is just one term. Oh, I need a little caret here. So this is just one term. We're summing over only one term. So this is just equal to 1 over 1 plus 1, which is 2, which is exactly what we wanted to show. Because if you plug in 1 over here, 1 over 1 plus 1 is 1 over 2. Now we need to state our inductive hypothesis. So, in this class we always use strong induction. So what our inductive hypothesis should look like is assume for all k less than n that, oh, and here we can actually use k because we're already using k as our index for this summation. So just to prevent any confusion, let's just change this to r. So we're assuming that for all r less than n, our summation from k equals 1 to r of 1 over k times k plus 1 is equal to, let me just put my thing here just so we can see what's being rendered. So we're assuming that this is always equal to r over r plus 1 from what we want to show. Right? Now for our inductive step, we need to consider the case when r equals n. So we need to consider from the sum from when k equals 1 all the way up to n of this summation. And we need to show, we wish to show that this can be expressed as just n over n plus 1. Right, so what we can do is we can break this sum up into two terms. What we want to do here is we want to use our inductive hypothesis somehow on our current sum. Right, so we know that by the inductive hypothesis this is true if there's an n minus 1 up here. So what we can do is we can turn this from the summation where the upper bound is n minus 1, and we can simply add on whatever we don't have. Right, so here if I sum from k equals 1 to n minus 1, the only term I'm missing is the term when k equals n. So I can just add that on afterwards. Right, so I would add on 1 over n times n plus 1. Right, and now I can use the inductive hypothesis. So by the inductive hypothesis, we can write this term from the sum from k equals 1 to n minus 1 as simply n minus 1 over n, which is what we get if we just plug in n minus 1 for n up in this closed form over here. So now we just wish to sum, so now just plugging that back into our original sum, what we're trying to find is the sum of n minus 1 over n and 1 over n times n plus 1. And I should put this on a new line, I think. All right. So yeah, so now we can just simply find the sum of this. And if we distribute this, and if we multiply the left term by n plus 1 over n plus 1, what we get is that this simplifies into let's see, the numerator would be n squared minus 1 plus 1, which would be just n squared. And the numerator is just n times n plus 1. And this just cancels out to equal n over n plus 1 as desired. And this would be sufficient for our inductive proof because we've shown that the base case holds, and for all n, we can show that this is true for n plus 1 as well. All right, let's move on. Okay, so now we have a broken induction proof, and we have to find exactly what's broken about it. So the proof goes, claim all horses have the same color. Proof will show that if S is any set of horses, then all horses in S have the same color by induction on the size of S. So here we're inducting on the size of S, so just keep that in mind. So base case, claim is clearly true for a set containing only one horse. If there's only one horse in the set, there's only one color, so all horses in the set have the same color. So our induction, suppose if T is any set of k minus 1 horses, then all horses in T have the same color. Let S be a set of k horses. We need to show that all horses in S have the same color. So this is the inductive hypothesis here, supposing that is true for any set of k minus 1. And now we wish to show that it's true for a set of k. So suppose S contains horses at h1, h2 to hk. The set S prime, made up of h2 to hk, contains only k minus 1 horses. So they must all be the same color by the inductive hypothesis. Similarly, all horses in the set S prime, which is composed of h1 to hk minus 1, must be the same color. Since S is a union of S prime and S double prime, all the horses in S must have the same color. So this is a little bit tricky. The way that we can actually, so what this proof relies on is that when we take the union of S prime and S double prime, we're actually using the fact that S prime and S double prime overlap to conclude that everything has the same color, right? S prime excludes H1, right? And S double prime excludes HK. And what we're saying is that because H1 and HK, and S prime tells us that HK matches color with H2 all the way to HK minus 1, right? And S double prime tells us that H1 matches colors with H2 all the way to HK minus 1, right? So our inductive step relies on the fact that we can say H1 and HK have the same color because they match with colors with H2 and HK minus 1, and H2 and HK minus 1 match colors with H1 and HK respectively. Right, so we're implicitly relying on the fact that there's some overlap between these two sets in order to conclude that H1 and HK overlap. So in general, this is true. But the case where this breaks is, what if there's no overlap between the sets? What if H2 and what if the set containing H2 to HK minus 1 is just completely empty? Right, and this actually happens when the number of horses you're looking at is 2. So when the number of horses you have is 2, then you split S prime into H2 to HK. Well, H2 to HK is simply just H2. And the set S double prime is H1 to HK minus 1. Well, H1 to HK minus 1 is simply just H1. Right, then, so yeah, if K is equal to 2, then, okay, well, I guess for this question we should first just give our explanation for how we found this case that breaks our induction. So we'll say that this proof implicitly relies on the fact that S prime and S double prime overlap in order to conclude that H1 and HK have the same color. Right? This is what we just discussed. So this proof, because of this implicit reliance on the overlap between the two sets, the inductive step does not hold for K equals 2. Right? In this case, S prime is the singleton set H1, and S double prime is the singleton set H2. Right? I'm just putting some arbitrary horses into these sets. Both of these satisfy the assumption, right? S1 only contains K minus 1 horses, only contains 1 horse, so does S double prime. And all the horses in both of these have the same color. So all the horses in both of these sets have the same color, but the union, we'll say S prime but their union does not necessarily have to contain horses of all the same color, since S prime and S double prime are disjoints. If you wanted to be specific, you could say, say H1 has color red and H2 has color blue, then S prime, all the horses in S prime have color red, and all the horses in S double prime have color blue. And their union, which is S, obviously doesn't have the same color. Obviously doesn't have that all horses have the same color, because there are two horses that have different colors. Okay, so that's everything. Hopefully everything made sense. I did want to cover a separate way of doing this question, but I don't want this video to run too long. But yeah, hopefully this was helpful.